Hello everyone, I'm Pooja and I welcome you all to another episode of Peep and EIP. Today we are going to talk about EIP-2537, Precompile for BLS 12-381. This is a standard track core EIP and is currently in draft status. It has been accepted as EFI. For those who are not familiar with the term EFI, it is eligible for inclusion. Following the EIP-centric model, EFI has been introduced to list core EIPs and track its progress, which in the future may undergo a network upgrade. To provide an overview and progress of EIP-2537, today we have Alexander Vlasov, also known as Shamta, and with him, we are also joined by James Hancock, the Ethereum hard fork coordinator, William Schwab, and Alita Moore from the Ethereum Cat Herders team. The ETH Magician and link for active discussion and EIP is provided in the description below. So without further ado, let me invite Alex. Welcome, Alex. Let us know a little bit about yourself and then we will dive into the protocol.
Yeah, well, a little bit about myself. Currently, I'm one of two co-founders of Matter Labs, and we, our main goal is scaling for public blockchains with zero knowledge proofs. As many of, or maybe some of you have heard, we have launched our mainnet called zkSync back in June. And we use zero knowledge proofs, snarks, Plonk as a proof system, and another Ethereum precompile to actually do our work and provide scaling benefits. But this is not that relevant, I think, for this discussion, but I would be able to answer any questions later on if there will be some. So if it's fine, we can just jump directly to the EIP description. It should be short, it will not be technical. And a little bit from historical perspective, initially I have proposed another EIP, which is 1962, which was a totally generic set of precompiles. So actually it was maybe just one precompile with huge functionality, which would allow different arithmetic operations over elliptic curves. And the goal for this precompile was like, make a generic solution which would serve everyone's needs. But then people had an impression that complexity of such precompile is enormous. And that's why it was cut in few parts. And the first one, and the simplest one, is 2537, which is only for BLS 12-381 curve. First of all, you should not mix the BLS signature, which is quite like commonly discussed construction right now. Well, BLS curve and signatures are two different deals and only shares the letter V for Dan Bonnet as one of the sources as far as I remember, but let's put it aside. So the main reason is to add the precompile, which allows efficient operations on elliptic curve, which first of all supports pairings and has a good pairing performance, and also which provides 120 bits of security. So this curve can be used in a long term. Right now, there is already one elliptic curve which supports pairing operations in Ethereum in the form of precompile, which is BN254 curve. And depending on the estimate, it has from 80 to 100 bits of security, which is fine. But since BLS 12-381 is kind of de facto standard and is like explicitly named in one of IETF drafts for signature schemes, for BLS signature scheme, decided that this is a good first candidate. So this precompile is quite simple, but it brings kind of three different flavors of operations. One of those, like first set of those, doesn't involve pairings, and this is just a standard set of operations over points on elliptic curve, which involves additions and multiplications. And those operations are already enough for some of the protocols. For example, bulletproofs do not need pairings at all, but still provide interesting instructions. So these operations are like for common use. There is also pairing operation, which requires curve with a special properties. So this is the main operation which is utilized by signature scheme, by zero knowledge proof verifications, by 16 proof systems. And also there is an auxiliary operation which is called the map to curve, which allows one to do to take a message or a hash of the message and map it from arbitrary 32 bytes to the point on elliptic curve in a secure way, because BLA signature scheme requires that the message should be mapped to the curve point. It is a requirement, and this operation is expensive and not well, and cannot be well expressed in terms of standard EVM primitives. So that's why it was introduced as a separate operation and also was introduced as a precompile and made efficient. I already mentioned like what constructions could potentially use an elliptic curve with pairing properties, but let's just go once again through it. First of all, it's everything which uses Zcash snarks in various proof systems. It can be for scaling, it can be for privacy solution. Maybe some of you heard about recent zero knowledge based game. It's actually, I would say, wonderful, and you should definitely try to play it. Well, as was mentioned many times, the BLA signature scheme requires to have a curve with pairing operation. So this can be used to various things like DAO governance, just rollups or plasma constructions where you have to get a signature from a large number of participants and verify it very fast and efficiently. It also will be required for cross-chain interactions. Like you can verify the validity of the block of another blockchain if validity just such validity check, for example, just requires a simple signature from majority of the validators. This idea was also part of like having a light client for ETH 2.0 when ETH 2.0 is launched as a smart contract for ETH 1.0. So it would be possible to get the data from ETH 2.0 beacon chain and refer to it from ETH 1.0. And it also kind of very good feature for ETH 2.0 deposit contract, because it allows a user to opt in to the validation of his public key, that it's well formed. So when he does the deposit from ETH 1.0 to 2.0, he will be able to access these funds in ETH 2.0, so that there is no problem that his public key is not well formed. So there would be no possibility to make a signature for such public key. So the user would essentially lose his funds. It's also used in more recent constructions like randomness beacons. An example is drand. I'm not that an expert in this field, but it's usable, and I think on-chain randomness is another important deal. And also another part is constructions which are, for now can be considered R&D, and those, for example, recent paper for vector commitments, and which can be used, for example, for witness compression in, for example, ETH 1.5 or whatever next upgrade of ETH would happen and require this feature. So let's get to the current state of affairs. So at the moment, this precompile is included in the code base of all major ETH 1.0 clients. And if someone would want to make a signature and do just anything using this PLS 1281 curve, there is a huge set of libraries which allows to do it for various platforms, various languages, and also various licenses, because it's also important. So this curve is indeed de facto standard, and there are a lot of tools to work with it. After integration, there was a fuzzing effort from guest team to fuzz the implementations between different clients, because clients use different libraries to actually implement what is required by the precompile. The interesting part there is, even while initially people viewed this precompile as like very complex and intensive math, there were actually no errors in mathematical part of all this code, but the only errors found during the fuzzing process were integration errors, like people didn't place proper constants in gas calculations functions, people didn't handle all the errors properly. So as it happens, arithmetic part and heavy math wasn't a problem at all. So for now, the state is all the clients have an implementation, and the only thing which is left is just declares that this precompile is included in Berlin, and have a Berlin at some point. And so we just activate it everywhere, and that will be usable by everyone. So it was indeed in 5 slides. So I can stop the screen demo. And
I actually keep it up, Alex. It's helpful. I think.
Okay, sure. Yeah.
And it's also, I wanted to say it's great working with you on the Awkward F call. So I enjoy when you come on and help your help and perspective as always. It's really
yeah. Thank you, James. Okay, I will also put a set of people, because I don't recognize everyone by voice. So.
Oh yeah. Go back a couple slides to the one where you talk about who needs it. Yes. So so the cross-chain interactions with ETH2, Filecoin, and Tezos, how is it because you're using the same version, or how does that how is it that it enables this kind of cross-chain stuff?
Well, it's more or less gets to the point how one can verify like validity of one chain in another chain. As an example, in ETH 2.0, it would boil down to verification of a signature of BLS signature. Well, too many BLS here, but of the verification of BLS signatures of validator set over the block header. And it will allow to attest to ETH 1.0 that this header is part of the canonical chain of ETH 2.0. This applies in principle to any proof of stake or proof of authority chain, which would use PLS signature over this curve as a kind of a seal of main and valid chain. I hope I tried to explain it.
Yeah,
enough.
So then if you can verify on your chain the validity of something, then you can essentially interact.
Well, yeah, I mean, if the chain construction is more or less following the standard pattern that there is some state, which is effectively a Merkle root of set of contracts, each of those having its own balances, and also there is a Merkle root of set of transactions, then you would eventually be able to just walk along this Merkle tree and, for example, says that, well, in this block there was transaction with these properties, and this would allow like some kind of the same as you would most likely do the deposit in ETH 2.0, that there was some transaction with some properties. So there was some set of funds locked in ETH 1.0, so it can be released in ETH 2.0. But all particular nature of interactions is up to some developer. First of all, you need to attest that this block is a part of canonical chain.
Yeah. So this puts the building blocks in, or the Legos, to allow this kind of stuff to happen.
Sorry?
This puts in the Legos or the building blocks for people to be able to do these sorts of things.
Yeah, it's such precompiles are not solutions for a particular problem. It's more like a tool which allows a large set of applications. Like I am a huge fan of snarks and also randomness beacon, but in randomness part, my knowledge is much more limited. I was only more or less following the construction by RSA, verifiable delay functions, and how it's incorporated in randomness generation. But looks like there are other solutions which are kind of simpler and would also want to have a BLS curve, which is required for them to work.
Yeah. Let's talk a little bit more, or I want to kind of get people who are users of the chain or developers of the chain a sense of, when you say it enables ZK rollups and privacy, what does that kind of benefit translate to users or to the people?
Yeah, well, this part is a little bit more technically involved, but as I made an example, there is already BN254 curve, which allows pairings and which allows ZK snarks using this curve, and this is what we actually do. I try to put the word capacity here. And
go like, in a little more into
to make it simple, when you make a zero knowledge proof, you have to express the statement you are proving as a circuit, which involves at a high level addition and multiplication gates. So, and to be able to run the efficient prover for such circuit, you need to have a set of roots of unity in your field over which you work. Usually the circuit is expressed over the prime field in this case, and roots of unity is a property of the modulus. In case of current curve, there are 228 roots of unity, the maximum size of the circuit. So if let's say you have, if you try to process transactions using zero knowledge circuit, and each transaction takes, for example, 1 million gates, and you only have access to the maximum of 2 in 28 gates, then the largest amount of transactions which you can process is around 256. This is for BN254 curve. The BLS-12381 curve has 2 in a power of 32 rods of unity, so it's 4 times larger. And it allows you kind of batch more transactions in one zero knowledge circuit, and verification costs for BN and BLS-12381 curves is roughly the same. So at the end of the day, when you do all the calculations, what is the final cost, you will get that you can get like 4 times the compression for the same amount of gas required on chain to verify the proof.
So in this case, efficiency translates into cheaper gas for users.
Yeah, if you just divide the total gas spent to verify the proof by the number of interactions or like transactions, which you can verify by one proof, you get like 4 times the efficiency in this case.
So, and this would be in like a layer 2 sort of something. So that would also end up being cheaper. Yeah,
I mean, this would translate to layer 2s having larger capacity per block. So effectively it would decrease the costs. But I mean, for layer 2s, there are other costs and consideration, so it's more complicated. But at the end of the day, if you run at full capacity and you just send a lot of proofs for verification, and you do it almost every block, then at the end of the day, your costs for end users will be 4 times smaller.
That's pretty good. I'd say. Is the privacy solutions kind of the same thing? Like it's more efficient or cheaper to do privacy solutions like what's the Tornado Cash or something like that?
I mean, for now, well, if you want to put an example of Tornado Cash here, it's a little bit more technically involved. You would want to run the recursion, but it's kind of the same. Like, no matter what is your construction, if you use zero knowledge proofs and you want to place, and if you want to prove the larger statement or to prove the statement over a larger set of small, simple chunks and substatements, it will directly translate to savings on the cost. There are also a few operations which are not available for BN254 curve, which is multi-exponentiation, which is simply doing a lot of individual point multiplications and then adding them up all together. If you use special algorithm for this, you get huge discounts, and such operation is a part of many verification procedures for zero knowledge proofs. So I would imagine that even for them, it would be an immediate, immediately benefit them for verification. And then if they decide to go into recursion, then the same capacity argument would also apply for them.
And recursive snarks is something that this BLS or this BLS version is
in principle, now you can do the recursion over just one curve, the same curve. The problem is that it's more computationally expensive, so there are trade-offs. So the recursion argument doesn't this curve is not strictly for recursion. This is de facto standard curve for all interactions listed here. But if we want to name it, there is another EIP, which is 2539, which is BLS 12, but 377 curve. A little bit different one, the only thing which is largely different is the modulus, a prime number which defines a field over the curve is defined. This curve is also known as the Zexi curve, and Zexi construction is from the Zexi paper, and we go in deeper and deeper in technical details. This curve is recursive composition friendly because it allows various tricks to make recursion cheaper. But I mean, we can go deep. We can go in this direction if you want, but I don't think it will be useful. We will just scare people away.
All right, but so just at least so I can be clear on it, there is your BLS version you're talking about. Would it enable something like 377 to happen later, or how related would that be?
Well, from my perspective, and from implementation of one curve or another, BLS 377 proposal is like copy paste of 381 proposal. Everything will be the same. ABI will be the same. Gas cost will be the same. All error all edge cases and errors will be the same. The only thing which will change is roughly 4 equations in the implementation, which are And these equations are usually not even hard-coded. They're just parameterized in the source code. So if this one is accepted, the modification for BLS 377 will take like maybe 50 lines of code to like provide an implementation for 377. It will not even change external interfaces, and clients would be immediately able to integrate it. So just from a perspective of how it is implemented in code, this is a small change of parameters. So nothing will change for external observer. But like it would be another building block for various constructions. But this is like there are various options what you can do now in the area of zero knowledge proofs. There is smaller set of options what you can do with zero knowledge proofs in Ethereum. So what I try to do is gradually increase this set of options. Because for now, for example, if you look at the Zcash, they're not limited by precompiles, and they can use any crypto they want, and they can use very interesting constructions like Halo. If you look at the Coda, they also recently introduced as their approach for efficient composition and like set of smart contracts, which would be possible with just purely zero knowledge proofs. So it's kind of extension. I try to extend Ethereum to support more and more primitives, which would eventually allow me and other people to build something which I cannot maybe imagine right now. For example, zero knowledge games are great. I was proposing it for some time ago, I think first on Zero Knowledge Summit last year, but I'm happy to see that someone has built it. So it's more or less a long road anyway.
So I have a quick question. You said that Ethereum, zero knowledge proofs in Ethereum is like limited a bit, and I'm wondering, well, first off, why, and like how is it different in Ethereum? Like how is this implementation different from, say, Zcash or something like that?
It's limited in the sense that, well, first of all, such computations, like an amount of computations required to calculate the pairing is quite large. It's few milliseconds if you run the native code on a recent CPU, which transforms to tens of thousands of gas in Ethereum. And like if you want to try to implement it in an EVM code, it will be prohibitively expensive in some cases and insanely expensive in other cases. Like all EVM primitive types are 256 bits. It allowed Zach from Adstack to actually implement the same BN254 curve, which was available in Ethereum as a precompile. He implemented it as an EVM contract. And it had decent performance before BN254 precompile was repriced, because implementations has improved. So the gas cost was reduced for this precompile. For BLS 12381 or 377 curves, it's even more difficult because they have to work over numbers which are 381 bit long. So they don't fit in a single Ethereum unsigned integer. So you have to do more and more tricks. That's why implementation of something like this as an EVM would be expensive. And it would be, first of all, difficult, and then it would be definitely more expensive than if you implement it in a native code, as an example with BN implementation showed. And no one wants to pay a huge amount of gas for any interaction. So such implementation has to be efficient. That's why it's usually implemented as a precompile, which is just a native code, which is just a function which is executed in native code and just bridged back to the EVM.
So have we ever considered, if I understand how it works correctly, have we ever considered doing like sacrificing some of the benefits of Turing complete like architecture for the benefit of like the more complex zero knowledge proofs? Is that something that we've considered?
Like I have at least two interpretation of this question. Like zero knowledge proofs as they are, in terms of zero knowledge proof circuits, they're not Turing complete at the beginning. So if you consider zero knowledge proof over some statement, the form of this statement for zero knowledge proof to be efficient has to be in certain bounds. This is part which is purely for zero knowledge proofs, which can be over different proof systems and different curves. But then you get to the point where you have to verify this proof. And in most of the cases which we discuss here, verification happens in Ethereum. So Ethereum itself should be able to do the computations which are required to do the verification. And these computations right now are involve running BN254 precompile, and later on they would be able to use this BLS12381 curve, which else is LC precompile. So this part has to be run in Ethereum and has to be as fast as possible. And right now there is only one curve. There maybe will be two in Berlin, but those two curves are not the only curves and constructions possible for zero knowledge proofs. There are other curves which we don't discuss here. There are other proof systems which have some different trade-offs. They can trade off bandwidths for speed, for example. And not all those kind of interactions are reasonable to have in Ethereum. So if you're like in most of the proof systems which are considered to be efficient in Ethereum, proof verification is a procedure which takes a constant time, no matter what is the size of zero knowledge circuit. There are other proof systems which have other asymptotical complexities. For example, in which proof verification is a procedure which takes a square root complexity over the circuit size, or even linear complexity over the circuit size. And those are not usable in Ethereum, but has other benefits. That's why there is a larger landscape for zero knowledge proofs, which is used by other chains. But we discuss Ethereum only here. So we try to bring the constructions which are reasonably efficient from both perspectives, running in a public blockchain, which is important, and also not having a full kind of power to extend this public blockchain in any way you want. That's why all those precompile inclusion procedures are quite slow. Even while there are other constructions in the wilderness which are also very interesting, but they will not be usable in Ethereum until more and more precompiles are introduced, or until something like 1962 is introduced, which allows any curves, any functions, and also high performance. But it was considered to be too difficult to include. Even so, there were 3 independent implementations which went through the fuzzy testing and didn't have any divergences. And also with a full spec to reproduce, but still wasn't sufficient as it happened.
So talking about Berlin, I'm curious to have a little conversation about the latest EVM-384 that came up in our last all core dev call. So would you be able to elaborate on like how is it going to affect, not affect, yeah, EIP-2537?
Before we jump into that, Pooja, can I say one last thing about this? That it seems like there's a wonderful world of ZK, lots of things that Ethereum and the community could use, and we're limited because the building blocks are either missing or too expensive.
Well,
Is that
you
kind of fair to say?
well, ideally, you should separate it here a little.
Okay.
Like there is a huge set of possibilities. Some of those are better suited for Ethereum. Some of those are not well suited for Ethereum. For example, size of zero knowledge proof using pairing friendly curves as, let's say, a few kilobytes, which is reasonable. And verification takes constant time. And let's say 500,000 gas, which is also reasonable. So it's kind of cheap. There are proof systems which have larger proof size, for example, Starks, where a single proof verification would take kind of like counting together the proof size and running the contract, which does the verification, which takes 5.5, as far as I remember, million gas for one block. So this feeds into the block, but more expensive. There are proof systems where the proof sizes would be even larger. So those are not suitable for Ethereum. We don't consider them. But even in a subset of those which are suitable, there is variety of choices, and those different choices would require different building blocks. Some of those are present in Ethereum, some of those are not present in Ethereum. And even while some blocks are present, there are better options of those blocks. For example, kind of for BN254 curve and this BLS12381. So this is kind of the separation.
I think that's really helpful. I can see, I see more of the expand, like the vision that you're expanding the possibility for what Ethereum can do, like just Bitcoin. And we're lucky that we have people like you pushing things like this so that they do get implemented and our share. And then Pooja, you could your question on the EVM-384 EIP-2537. It came up on the last call, and you had like a space to respond about it since then.
Yeah, right. So I was curious, like, how is it going to affect EIP-2537? Like, with the discussion in the previous all core dev call, I'm not sure if it is like how we are going to take, are we considering both, or how is it going to affect? Can you just let us know pros and cons of this versus that?
Yeah, I mean, I definitely cannot answer how it's going to affect, because I'm not the person who does the decision. But from what I've seen, I didn't dig very deep, so there are maybe some other factors which I don't count. Right, in short, right now the performance difference is a factor of 3. So this would affect like anyone who would want to use and like a curve like BLS12381 implemented either in native code or using this new opcode. So it would force people to pay 3 times the gas. Also the comparison which was present there, it was between kind of generic implementations of both, which is a reasonable comparison. So if people would start to do optimizations on both sides and they go to the extreme limits, I think the ratio will stay largely the same. So it will be 3 times in overhead, no matter if everyone goes to all the way down to assembly to implement basic operations. So I believe that the ratio will be somewhere around factor of 3. I also didn't look at some internal parts of this comparison because there are operations which could have, like recent benchmarks for EVM opcodes. It's not exactly the pairing operations being implemented. It's kind of the simulation of this by operation counts. So it's like doing the same number of operations, primitive operations, and to see how long it takes. So there is no implementation, there is no full implementation there. There is no control flow, and I don't know how difficult it would be to implement it. So it's still in research. There are also other parts, which, for example, subgroup checks, which I know how are implemented in 1962, which was a baseline for them. And I don't know how they were simulated in EVM opcodes. And this difference can also be quite substantial because they take some like up to 40% of execution time. So we will see how this progress goes, but my prediction is more or less that it will be penalty for end users from performance perspective, somewhere around the factor of 3, if someone would want to kind of force that such operations would be implemented using new opcodes instead of native code.
And more penalty on performance translates to higher gas costs.
Oh, yeah, yeah. I mean, I thought this was kind of obvious, but yeah, I mean, if we assume that any second is some amount of gas spent, then yeah, it would directly transform into higher gas cost for any operation.
Thank you. And like, I hope that these comparisons would be coming up soon, and we will get to know like how is it going to go ahead, like EVM 384 or this one or both. How you?
Well, I can give my perspective on that, Pooja, for at least from the hard fork coordinator side.
Yeah, please go ahead.
I think EVM 384 is a good direction, but is it a reason to delay other good things? So I don't think anyone's decided anything. That's kind of where I view this as another good thing that is pretty far along and can benefit and give value to both devs in the scope of what things they can do and users in that it's cheaper to do things that they want.
Yeah, well, it can be, I mean, for this particular choice of, like, I don't know what's happening with hard fork coordination in a sense. Is there a plan to have it at some point? Is there a deadline to have it, or you can delay it more and more until all this resolves, but which effectively leads to like not having features which could have been there already. But like purely from a technical standpoint, maybe it's kind of useless for 384 bits, but it can be usable for other cases. Like for 384 bits, as it happens, there is definitely an overhead in crossing a boundary between the EVM and the code which actually does field addition or Montgomery multiplication. But if you go to the larger field size, for example, let's say twice larger, this ratio will definitely change. And maybe for field sizes which are roughly 768 bits, let's say, this ratio will be such that an overhead will be not 3 times, maybe it will be 30%. And then it would definitely make sense to have a universal solution over particular ones. Maybe just not the best choice for 284 bits. But it's kind of another level of research. I don't know if people working on this, especially AXIC, will have a time to try it in a short term. But maybe it would be kind of a niche for such implementation using the opcodes. It's I didn't like. It's just my idea. She just had.
Cool.
Yeah, that
I don't
is.
know. That seems good to me, guys. This has been a really awesome conversation. Thank you, Alex.
Yeah, both of you. Thank you, Alex. Thank you, James. This was really an interesting conversation, and we get to know more about this particular EIP. With this program, we are hoping that it would be useful for community to learn and ask questions directly from the author. So that's what we are trying to achieve here. And I think that we have achieved some of the questions that we received has been answered. So I thank you all for joining us today. And with that, we have reached at the end of the episode. But as I understand, there is another proposal authored by Alex, which is under discussion for Berlin, that is EIP-2636. So I hope to see you again on this show to learn about the proposal. And for those who are watching us on YouTube, I hope to see you all in another episode of Peep and EIP with another proposal. So if you have any protocol that you would like to understand or ask questions with the author, please comment in the comment section below, and we'll try to invite the EIP author on our show. Thank you everyone for joining.
And Alex, where would be a good place for people to follow you or the Research of Matter Labs if they're interested?
Well, we're not that active on social media. There is a on our website, which is easy to Google. There are links. Well, there is a link to the GitHub channel, and usually when we have something, we write a blog post. But all the work is happening on the GitHub, and we're not that active on social media. But yeah, you can just try to find us on Google, the Matter Labs. You will find it easily, and you can check the materials. And a few hours blog posts with quite a 3 of them were quite recent on Medium. Other than this, I don't think there are good sources. Or if necessary, you can reach me in private message on Twitter or in the Discord. I have the same handle everywhere, so you can just PM me if something.
Yeah, we will add that in the description below.
Mm-hmm. Okay.
Thank you, everyone. Thank you for your time. Have a great day.
Okay. Thank you, everyone.